Hi, my name is Sean Gibbons. I'm an associate professor at the Institute for Systems Biology, and I'm here today with Dr. Alex Carr, who is a postdoctoral fellow in the lab. Our lab studies the human gut microbiome, and Alex has a paper that just came out on understanding infectious disease risk in the microbiome through modeling. So to start off, we focused on a particular pathogen called Clostridioides difficile. It's an opportunistic pathogen, so it can kind of live in two different life phases. It can be a normal commensal that sort of sticks around in your gut at low levels, but it can also cause disease. Alex, can you tell us a little bit about C. diff and its impact in the U.S.?
Yeah, totally. Yeah, C. diff is actually one of the most common hospital-acquired infections, and it also is particularly a problem when individuals are taking antibiotics or they have experienced any kind of event like diarrhea or anything that can disrupt their native microbiome. And so in the hospital setting, when you're given antibiotics, potentially for something unrelated to the microbiome, whether it be surgery or something else, if you have C. diff or you acquire C. diff while you're in the hospital, in the absence of any competition in your gut microbiome following antibiotic use, it can bloom and lead to severe illness and in some cases death.
Yeah, I mean, C. diff is an opportunist, and it's able to kind of sit around and wait for a long period of time by getting in, living as a commensal, and then eventually, yes, causing these terrible infections. But little is known about this commensal lifestyle of C. diff. Like, how does it get in? It seems to colonize up to 30 or 40% of all people walking around in the world, and yet it rarely strikes to actually cause disease. So it's just lying in wait in this big reservoir of people. The rates of community-acquired C. diff infections are on the rise, even while hospital-acquired infections are falling. So we really need to address this problem of commensal carrying of C. diff. So what kind of tool did we bring to the table here for trying to understand this commensal niche of C. diff?
Yeah, that's a great question. Yeah, to be able to better understand the susceptibility of individuals for colonization, we leveraged a metabolic modeling tool developed by a former postdoc in the lab, Christian Diener, called MyCom. And this tool allowed us to be able to predict the growth environment of C. diff in the microbiome and be able to predict individual susceptibility to C. diff colonization, as well as the sort of interplay between C. diff and the commensal microbiome.
Yeah, so MyCom has proven to be a fairly useful tool in exploring these microbe interactions in complex communities. And I should say that Christian Diener is also a senior author on this work and helped kind of supervise this work. He's now an assistant professor at the Medical University of Graz in Austria. So, like you say, you can simulate these microbiomes, the metabolic environments of people's microbiota, and kind of add in C. diff in an invasion type of assay. How do we validate that this predicted growth rate of C. diff in the model is actually real or applicable to the real world?
Yeah, another great question. Yeah, I think something that comes to mind is that all models are wrong, but some are useful. And so I think what makes this model useful and the way that we tried to validate the model outputs was to take publicly available data where we had known instances of C. diff colonization, and then compare the model predictions for the C. diff growth to the whether or not the individual had C. diff, and we found that using in vitro data, where we had microbes grown in test tubes, and we're able to observe whether or not C. diff was growing. The model accurately recapitulated the results of these experiments. Additionally, we had 2 time series from individuals that tracked their microbiome composition over time for about a year each. And in both instances, the individuals had an event that led to diarrhea, and then one of them was subsequently colonized by C. difficile. And our model accurately seems to capture this transition from being C. diff being absent to then being colonized. And so, yeah, being able to validate the model using these different data sets has given us confidence that our results are realistic.
Totally. I mean, I was very impressed with the time series, right? You see that you try to invade this person's time series with C. diff prior to this colonization event, it just will not grow in the model. But as soon as the diarrhea event occurs, suddenly you can predict growth, and it matches the abundance of C. diff that we measure. You know, there's no way they give you permission in a clinical trial to give someone C. diff. That's like a dangerous intervention. But it was lucky that we had this instance of capturing in the wild an occurrence of someone actually being colonized by this bug. So we can predict C. diff's growth in these models. There's some hints that it seems to be an accurate prediction. What do we learn about its niche in these different people's guts through looking into the guts of these models?
Yeah, one thing we found that's very interesting is that C. diff, based on our predictions, seems to have a fairly flexible niche and can leverage a variety of different strategies to establish itself in the gut microbiome, which might explain why it's so good at colonizing individuals and can then develop into these infections. In particular, we found it seems to be leveraging, in the model, it's leveraging metabolites that have been shown to promote its growth in the clinic, like metabolites like succinate and trehalose. But it also seems to be, its niche seems to be really context dependent on the community structure.
Yes, and I should also say, there were a couple of different niches that kind of popped out in these clustering analyses, but one was it just didn't grow in some people, right? So there's a certain proportion of the population, maybe half, where you try to invade their model with C. diff and it just falls off. It doesn't grow. It can't get in. So that's interesting. There's some people who are resistant, and then a subset of are susceptible, but in those susceptible folks, there seems to be different ways for C. diff to make a living in these different people. What did we learn about the interactions with the commensal microbes in C. diff in these different contexts?
Yeah, one thing we found is that we maybe would have expected that in general the interactions were either positive or negative, and in some cases that seemed to be true, but moreover we found that a lot of the interactions were very context dependent. So in some cases you would have commensal microbiota competing with C. diff for a particular metabolite or a set of metabolites, and in other contexts they might cooperate. So it really, I think, drives home this idea that you can't always frame the commensal microbes as either always being good or bad. It really is more dependent on the overall community composition than the presence of one or two particular bugs.
Yeah, I remember it being very, very slippery. A bug could be feeding C. diff succinate in one microbiome, but it could be competing with it for succinate in another person's microbiome. And then some commensal microbes seem to be closer to C. diff's growth niche. They ate similar things, and they were perhaps suppressing C. diff. But there are other bugs that seem to eat very different sets of things, and yet somehow they were also still competing with C. diff for certain key metabolites. So, there was no one-size-fits-all, one bug is always good, one bug is always bad for C. diff susceptibility across people. It was this emergent property of the entire ecosystem that you only get from this kind of modeling.
Yeah, I think it really speaks to the complexity of the interactions in the microbiome, and that it isn't always easy to really pin it down to being, having one or two causative factors.
Totally. So then the next question is, can we intervene to take people who are C. diff susceptible and make them resistant? So what was the first thing we tried to kind of look into this?
Yeah, so what we did following the initial validation was we leveraged data where we had individuals who had a CDI who then received an FMT and then became more resistant to colonization. We took this data set and we want to ask, like, could we use a publicly validated and available probiotic and assess its efficacy in the context of this modeling framework? And so we use this probiotic called VE303 from a company called Vendata. And this particular probiotic is composed, I believe, of 8 different strains of these closely related Clostridium. And they have already shown in mice and in some clinical trials that this seems to be pretty efficacious. It can reduce the incidence of CDI in mice and seems to be well tolerated in people. So we took this cocktail and were able to identify metabolic models for a majority of the strains. And using this invasion assay framework, we introduced the probiotic alongside C. diff in these individuals who were receiving FMT before and after. And we found that this particular probiotic, in line with the published data, is able to, or was predicted to, suppress the growth of C. diff in many cases, and that the mechanism of action seemed to be a competition for shared metabolites, or for a shared niche.
Yes, yes. So yeah, this particular therapeutic V303 from Vedanta, it is going into phase 3 trials now. So they had their phase 2 successful results published. So it was kind of cool to take this known product with known efficacy and look at its effect in the models. And of course we saw that, yeah, on average it was competing with C. diff and had a suppressive effect on the growth rate in the modeling. But then some people showed a stronger effect of the probiotic in their guts than others. There were kind of responders and non-responders that popped out. And so that kind of a phenomenon, where an intervention works better in one group of people versus another, that requires precision medicine, right? It requires some sort of precision modeling framework to identify non-responders and try to rescue them, to rescue their response. So how do we think a little bit about this in looking at other commensal interactions and suggesting other possible probiotic organisms that could be added to some future intervention?
Yeah, it's a great question. I think one of the utilities of this modeling framework is that it does give us the possibility to explore other possibilities without having to do experiments. And so following the results that we got with VE303, we felt really confident that the model might be able to, we might be able to use the model to explore other interactions. And in particular, I was interested in understanding how more dominant genera in the microbiome might be playing a role, because the introduction of VE303, in some cases, it is a perturbation that is impacting the overall composition. And so, in exploring the relationships between the abundance of the other dominant genera and the growth of C. diff, we found that, in particular, the Bacteroidetes, organisms like Bacteroides and Phocaea-cola, their presence seemed to really lead to suppression of C. diff. And moreover, we had seen that this effect seemed to be true both in other data sets as well, like the in vitro data. And so looking into that a little bit further, we found that while the organism Phocaea-cola doesn't seem to share a direct niche with C. diff, its presence does seem to impact C. diff's ability to colonize. And it may be that it is having sort of indirect effects by, supporting the growth of other commensal organisms that do compete with C. diff. And so exploring this relationship, we found that, introduction of some of these genera, like Phocaea-cola, could be an additional means to make, modify these cocktails and make them even more efficacious than they already are.
Totally. Yeah, I mean, I remember when we were first looking at this, there was a kind of if it isn't broke, don't fix it phenomenon where you added the VE303 cocktail to someone who was already resistant to C. diff invasion. And by depleting the relative abundances of the other commensals, including things like Coca-Cola, that would actually increase your susceptibility. And so by looking at those correlations, you were able to kind of map out what might be other promising taxa to include in this cocktail. So we're excited about this as a general framework for trying to design precision probiotics or even dietary and prebiotic interventions that target opportunistic pathogens. C. diff was the first try here, but there are other opportunists that live in the gut that cause disease that could be addressed through similar means. So this is the first step on a longer path towards clinical translation, but I thought this was a really fun and exciting paper. So congrats on such a cool paper.
Yeah, thank you, Sean.